In Lecture 2, we talked about faults that happen when rock deforms in the Earth's crust and breaks. In this lecture, we're going to talk about what happens after the Earth breaks. Because when a piece of lithosphere cracks, there is a sudden release of energy right along that fault line. And as this energy ripples through the lithosphere and the crust, the rock then suddenly snaps back to shape in a process called elastic rebound. And if we have these rocks under a stress that shift along a fault, we get these waves of energy that we call earthquakes. And just in case you forgot what a fault is a break in rock. And one side of the rocks on one side of that break move relative to the rocks on the other side. Well, when we have an earthquake, there are some important little features to find out. One of these areas that you want to identify is known as the focus of the earthquake. And the focus is where the first motion of an earthquake occurs. A lot of times the focus is in the rock itself, which is different from something called the epicenter of an earthquake, which is the spot on Earth's surface where the earthquake starting point is. So the motion happens deep underground or sometimes shallow under the ground, and the epicenter is that spot on the surface where the earthquake happens. For the most part, if an earthquake happens on a continent, it has a shallow focus. Shallow focus means it is near the surface of the rocks. Whereas earthquakes that are happening in a subduction zone, usually where an oceanic plate is submerging under another plate, tend to have deep foci, or a deep focus. And the deep focus, is deep underground. It doesn't cause as much damage because it is farther from the surface. And so shallow foci is close to people because we live on the surface of the earth. Here's a diagram just showing you the different parts of an earthquake. Right along here, here's your fault. You can see the direction that the two plates, or in this case the fault blocks, are moving. Alright, at our fault. Here under the earth, right along that fault line, it's a cross section here, is the focus. This is where the earthquake has started. So this is where the earthquake starts. And then directly above it, right here on the surface, directly above the focus, is the epicenter, which is the spot on Earth's surface where it is. And that's what we usually try to find, is we try to find where the epicenter was, and we know the earthquake happened under the ground. Coming out from the focus in all directions are things called seismic waves, which we're going to talk about in a minute. Seismic waves themselves are waves that travel through rock. In this case, we call them body waves. Seismic waves are waves that travel through a medium, and a medium is a substance. So they travel through the main chunk of that substance. There's another type of seismic wave called a surface wave, and they travel along the surface of a medium or a surface of a substance. All right? And the surface waves have a stronger effect at the surface. They influence stuff on the surface of whatever had the earthquake or whatever the wave is passing through. Whereas the body waves deal more with the interior. So as we have two rocks along a fault slip into new positions, break into new positions, hit each other, energy is released, and we call this release of energy seismic waves. And they go in all directions from the focus, as you saw in that last picture. There are two types of body waves. Remember, these travel through the rock. All right. The first is a P wave called a primary wave, also called a compression wave. The wave that causes the rock particles to move parallel to the direction of the wave. So it's a squeezing of the rock. And as this P wave moves through, the rock gets squeezed and then snaps back into place. It is the fastest moving wave, and it goes through solids, liquids, and gases. And the more rigid, the more solid the material, the faster the wave is. A compression wave is kind of like a sound wave. If you put your ear on a table and have somebody lightly tap the table at the other end, you can hear the tap a lot louder than you can if your ear's not on the table. And that's because the sound wave travels faster through the solid table than it does through the air. And so the sound gets to you faster. It's also why sound travels faster on water. If you've ever been out boating, you can hear what people are saying on shore a quarter or half a mile away from shore, because the sound waves are going through the water and you're hearing them that way instead of going through the air. The second wave is called the S wave, called the secondary wave, also known as a shear wave, and it moves up and down in a side-to-side direction perpendicular to the direction of the wave. All right, so it's more disruptive. However, it only travels through solids. It cannot travel through gases or liquids. All right, it's also the second fastest seismic wave. And what we do with this knowledge of these waves is we perform a science called seismology, which is the study of earthquakes and seismic waves. So you got the size and the seismology. And then the person who does it is a seismologist, and they try to locate, record, measure earthquakes. The instrument we use is a seismograph. There's that word, or that prefix again, seismograph, seismologist, seismology. And the actual piece of paper, the actual piece of data we look at is called a seismogram. And the seismographs themselves, they record the motion of the Earth in three directions: the north-south direction, the east-west direction, and then the vertical direction, or the up-down direction. Fast waves come to the seismograph first, and so they get recorded first, and then come the shear waves. And usually what you end up seeing is a big spike after the S waves get there. So if we had a seismogram, it would be going, and then we'd get a P wave, and it would fizzle out, and then it would get big, and we'd get the S wave. And what we'd end up with is here is where the P wave hits, here is where the S wave hits. And I should have wrote an S instead of a W, but we get the P wave right here, the S wave right here. So you see the P waves get there first, and then the S waves get there. And then over time, those waves dissipate. By taking a look at the amount of time between the P wave and the F wave, the P wave and the S wave. So we analyze the arrival times of the P and S waves. We come up with something called lag time. And lag time is the difference in time from the P to the S wave. So the longer it takes for the P wave and S wave to get there, the farther away the earthquake is. And if we do this from 3 locations, I know it says several here, but you need at least 3 locations, we can figure out the location of an earthquake. And we do this by drawing a circle from each location, and there should be one spot where all of the waves or all of these circles hit. So let's say we have an earthquake. Alright, so one city, it is this far away from. A second city, it is this far away from. That's narrowed us down to 2 points. It can either be right here or right there. And then if we have a third city, we can then find out how far away, and like this area right here is where all 3 graphs kind of meet, and that could be our epicenter. No, that's kind of a weird little thing. Computers have helped immensely because now we don't have to rely on people trying to draw circles. Now, because S waves cannot pass through liquids, there are these things called shadow zones, and a shadow zone is an area that only receives, missed my E, I, B, S, receives P waves. Alright, and they occur on the Earth. We'll see a picture in a minute. And the P waves also have a little shadow zone because of the bending of the waves as it goes through Earth's interior. So what happens is some parts of the Earth are more solid than others, and so as the speed of the wave changes, it bends a little bit. All right, we'll get back to the shadow zones in a little bit. We'll see another really good example, a good diagram of those. The surface waves themselves, they only come from shallow earthquakes or energy when the P waves and S waves reach Earth's surface. Right, they are the slowest moving seismic waves. They only hit pretty close to the epicenter, but they cause the most damage, and the whole reason they cause the most damage is the surface is where we build stuff. Alright, so we build stuff on the surface of the Earth, and when the surface of the Earth starts moving, that's when we run into lots of damage. One type of surface wave is the Love wave, named after a scientist named Love, and that causes a side-to-side and perpendicular motion of the surface of the Earth. You can actually see the Earth ripple. So here's that diagram I was just talking about a little bit ago. Our P waves, you can see the compression right in there. P waves are compression. S waves move perpendicular and are a shearing force. So here, the ground, they move side to side, cause ground to move side to side. And then the two surface waves outlined here in red, these are surface waves. Two surface waves, Raleigh waves, cause the ground to roll, like ripple almost. And then love waves just send the ground in like perpendicular spikes. It's like an S wave and a Raleigh wave combined to make this love wave. And here we can see the shadow zones. Like if the earthquake is happening here on the Earth, in order for a place on the other side of the globe to record the earthquake, it's got to be able to get either a P wave or both a P and an S wave. And a certain amount of the globe will not get any S waves because the waves would have to travel through the outer core, which is liquid. And then because the outer core is liquid and the inner core is solid again, as the P wave travels, you can see it bending a couple of times. So we get these two little spots where you can't even detect a P wave. If we mapped out most of the recorded earthquakes of the last few hundred years, what we notice, they tend to occur right along plate boundaries. These boundaries in blue are divergent boundaries. Here's the mid-ocean ridge, the mid-Atlantic ridge. There's Iceland, where the two plates are spreading. Around here, this purple area are convergent boundaries, convergent oceanic boundaries. That means they contain at least one oceanic plate. And then this whole pink area here are the continental environments. And you kind of see that's where India is crashing into Asia over there, where the Himalayas are growing. But one of the big things about this whole area right here has a lot of earthquakes and volcanoes, and that is known as the Ring of Fire. So once in a while we do see earthquakes that seem to be far away from boundaries and in the middle of a plate, but generally those occur for either reasons. This is Hawaii right here. There's active volcanoes there, which has molten lava and rock, which could cause the ground to move. In places like where we live and down in the Mississippi River Valley, we found really old ancient fault lines before the continents got put together like they are now. So rocks could still be shifting and moving down deep in the earth. So every once in a while we get an earthquake. Nothing as devastating as they get in California along the San Andreas Fault or in some of these other areas. There was that big earthquake that hit Haiti, which is right over here a while ago. Well, we got a bunch of plate boundaries right in here as well. So earthquakes and plate boundaries kind of go together. Now when we measure earthquake, we can measure it two ways. Magnitude, which is how strong the earthquake is. Magnitude deals with strength. Alright, the stronger the earthquake, the more energy. Alright, so this looks at more energy involved. So more energy means more ground motion. We use something called the Richter scale, which has evolved into the moment magnitude scale, and what it does is it looks at how much the ground has moved. So when you hear an earthquake is a 4.5, that's usually a Richter or moment magnitude scale, and that gives you an idea of how strong it was. Alright, it is a logarithmic scale, so each number on the scale is 10 times more powerful than the number before it. So a 4 on the Richter scale is 10 times more powerful than a 3, but 10 but 1/10 as powerful as a 5. So that's why when we start hearing about earthquakes that are measuring 7s and 8s, they're so deadly, because an earthquake that is an 8 is 1,000 times more powerful than an earthquake that is a 5. So the main difference between the Richter and moment magnitude scale, moment magnitude looks more directly at the rock properties. So it is a little bit better scale to use nowadays than the Richter scale, although for the most part they come up with a very similar answer. The moment magnitude just takes the rock properties a little bit more into account. The other way to measure an earthquake is intensity, and intensity, we talk about how much damage is caused. Alright, so there's more damage possible where people live. So even though we could have a really huge earthquake in the Pacific Ocean of like a 8.2 on the moment magnitude or Richter scale, it might not cause as much damage as, say, a 6.2 earthquake in San Francisco, which would be 1/100th as powerful as the one I just talked about happening in the ocean. But there's more damage that can be caused, and the Mercalli scale is given a damage level between 1 and 12 and given Roman numerals, and the higher the number, the more damage. In class over the next few days, we're going to be doing a couple of different epicenter location activities online, and we'll probably get a chance to look a little bit more in depth at both the Mercalli scale and the Richter/moment magnitude scales to get an idea on the intensity and magnitude of earthquakes. Next up in the lecture series, we're going to start talking about volcanoes, which themselves are sometimes related to earthquakes.